We might not notice, but tremendous technology and mind-boggling science constantly surround us in the products we use every day. Behind their practical use lurk hidden histories, dramatic discoveries, and awesome experiments. They are wicked inventions. Coming up, ice skates, the Swedish steel secret behind these magical blades. The Archimedes screw. What is the connection between this ancient Greek device and your plastic mobile phone? Guitars. Which ancient civilization first used a guitar, and why is a dovetail so important to its production? We reveal the surprising science and amazing manufacture behind these wicked inventions. Modern ice skates are used on ice rinks all around the globe, but just how were they first introduced?
Everybody loves ice skates. I mean, they're an excuse for us to make a fool of ourselves. And it seems like our ancestors loved skating on the ice as well, because the first ice skates that we know of date back to around 5,000 years ago, and they were made out of the bones of large animals.
Examples of these large animals are horses, ox, or even deer. These bones were attached to the skater's feet with leather straps. However, these skates would have required a pole with a sharp metal spike that would be used for pushing the skater forward. Many believe that the Dutch played a big part in the development of ice skates. This is because they were the first to create sharper edges on steel skates, primarily to aid movement. As time progressed, we saw little development of the ice skate until the first organised skating club was created in Edinburgh during the 18th century. These clubs used natural frozen water to host games and smaller races. In the 1840s, we saw early attempts at the construction of ice rinks, a designated area where people could skate. Just over 30 years later, the world's first mechanically frozen ice rink was opened. It was named the Glaciarium and was located in London. We then saw the slow rise of ice skates in sport. Figure skating, which is the performance of freestyle trickery on ice, was first contested at the 1908 London Games before becoming the first sport on the Winter Olympic programme. We now see other sports played on ice such as ice hockey and speed skating, both of which now feature in the Winter Games.
So even though we've been skating for thousands of years, the actual science behind ice skating has been the topic of quite a lot of debate because there are so many things that go into it. There's pressure, aerodynamics, friction, even the molecules of the actual ice itself can play a part.
The safety of skating depends on the roughness of the ice, the design of the ice skate, and the skill and experience of the skater. Ice rinks allow ice skating all year round, but just how are these essential skates made today? There's a great deal that goes into producing a professional pair of figure skates that can stand the test of time. Rydell Skates, based in Minnesota, USA, have decades of experience in doing just that.
Our company was started in 1945 by Paul and Soph Rydell, who happened to be my grandparents, and his design of his ice skates started to become very popular, so we've grown since that time, and now we make and ship skates all over the world.
First in the production process is the cutting of all the fabrics that will go together to form the boot. Dies are used that are shaped to each of the relevant fabric parts of the boot. They're a lot like cookie cutters and are placed onto the fabric before a hydraulic press pushes down, leaving freshly cut to shape fabric in its wake. Once each of the parts have been cut, we can begin the fitting stage. First, a label is stamped onto the newly cut inner lining of the boot. This contains information such as shoe size and width, as well as the date it was manufactured. Markings are then drawn onto the boot materials that will guide the sewers in the sewing stage and also indicate where the eyelets for the laces are to be fitted. The sewing can finally begin. The tongue parts of the shoe are reinforced and sewn. This reinforcement will sit in the toe area of the finished ice skate, where extra strength is needed. The separate fabric parts of the boot are then skived or beveled. This essentially makes it easier to sew these parts together, as it thins out the part of the fabric where stitches will be made. Ankle padding is then added to the lining. It is important that these skates are as comfortable as possible for the figure skaters that wear them, as well as providing as much protection as possible. These parts are then placed into a press in order to better bond the padding to the lining. As the sewing machines continue to work their magic, all of the inner linings and leather uppers of the boot are sewn together. Bonding cement is pasted onto all the parts of the shoe, again to increase their strength and greatly improve the durability of the ice skates. These parts are then placed in a heat press to firmly bond everything together. Washers are fitted that will go on to the back of the hooks for the laces, and these hooks are then installed. Foam pieces are then fixed to the ball area of the shoe for extra cushioning. Figure skaters will spend a lot of time using this part of their foot, so this little bit of foam is particularly important.
Staying abreast of what the athlete needs in terms of product for fit, comfort, performance, longevity, support is going to be probably some of the bigger challenges that we have to address.
The toes are then sewn together and rubbed out, and our pieces of fabric are at last looking more like a shoe. The lining is then secured with spray cement, and even more foam cushioning and reinforcement is added. Once the eyelets that the laces will pass through are fitted, the boot can be laced up with temporary lacing that will keep everything in shape during the next stage. Next up is the lasting process. This involves taking the newly sewn pieces and forming them around a foot mould, more commonly known in the business as a last.
The last gives the skate the consistent size, width, dimension, height, and so forth.
Once everything has been fitted around the last, the boot is placed in a heater, which will cause the leather to hold the shape of the last. The bottoming stage is next. Here, the outside of the boot will be attached to the bottom. Very strong adhesive is applied to the bottom of the boot, and then the outsole is firmly pressed into place on a sole press. At this point, the last can be removed from the boot. The outsole is then stitched and trimmed to shape. Using a heater, any loose or slightly too long threads are literally singed away, keeping our boot perfectly tidy and presentable. We're at the finishing touches of the boot now, where a logo can be fixed to the heel. The boots can be laced up, cleaned and boxed up.
We have 5 different major departments that our product goes through, upwards of potentially 125 different manufacturing steps that our product can go through in all those departments. Our in-process time from the time it gets cut to the time it gets packed in a box can be approximately 10 days. We're going to be, somewhere in that area of probably 35 to 40,000 pair built and made in this factory.
We've forgotten something though. The all-important blade that will turn these boots to ice skates. These blades are all manufactured off-site by Step Skating Blades, based in Canada. They are made with the highest grade Swedish stainless steel, meaning our ice skates can skate for miles. With the blades attached, our ice skates are complete, ready to hit the rink and to create some real figure skating masterpieces. Ice skates, truly a wicked invention. It is an ingenious device to move water that was once used to irrigate one of the 7 wonders of the ancient world, and can now be found in all sorts of industries, from generating electricity to helping clean our water supplies. It is the Archimedes screw. Historians date the first evidence of this broad threaded screw device to around 250 BC, and it is so named because tradition suggests it was invented by the Syracusan mathematician, philosopher and scientist Archimedes, who employed it as a ship's bilge pump for moving water from inside ancient galleys.
The Archimedes screw was named after Archimedes, a Greek inventor, but it's entirely possible that he actually improved on earlier designs that have been found that did a similar job, and his was the popularization of it. Oftentimes in history, the person who popularized it is the person who is considered the person who has invented it, even if this is not always the case.
Regardless of its origins, the Archimedes screw represents the combination of 2 common simple machines, the inclined plane and the cylinder. The plane wraps around the cylinder, making a common screw shape. However, the Archimedes screw is not intended to drill into anything. Rather, the rotation of the screw forces liquid or small materials upwards. This movement is intended to process liquid, irrigate land, move corn, and many other uses.
The Archimedes screw works by having a cylinder, and inside you have a helical structure which has long planes that allow it to bite into something. Except in the Archimedes screw, it's a very thin central section, and the planes themselves are very wide. They're also very closely matched to the size of the cylinder. What this means is if you take it and tilt it at a 45-degree angle, the planes start to form, will belong with the cylinder, a sort of cup, that as you screw, or turn the screw, those cups move slowly up the cylinder. As those cups move slowly up the cylinder, that allows whatever is inside to be transported. This could be water, liquids, whatever you need to move from a lower plane to a higher plane, and with relatively little effort.
It has been suggested that even before Archimedes' time, a water pump based on the Archimedes screw principle was used to irrigate the steppe vegetation of the legendary Hanging Gardens of Babylon, and today its usefulness can still be seen in a wide variety of applications, including in the guise of an auger, a tool that creates holes in the ice for fishing on frozen lakes and seas. With its ability to drill into ice, how closely related to a wood screw is the Archimedes screw?
The difference between a wood screw that you use to screw into wood and an Archimedes screw is one of exaggeration. In an Archimedes screw, the bits that you would bite into the wood from a wood screw are much, much more exaggerated. So you have that thin central pillar, and then the actual planes on the outside are much larger compared to the central part. As it turns, you could argue that it is pulling its way through the water, but because it remains stationary, it pulls the water up. And the screw works best when it has large fins and a large diameter.
In modern industry, the Archimedes screw can be seen working in a variety of environments, not just moving water. Reversing the screw's action is used to produce hydroelectricity, with the flow of water spinning the screw, which in turn can power a generator. Screw conveyors move loose material like grain in agriculture, and many of our plastic products are made with the help of the Archimedes screw. For instance, most of the world's mobile phone cases will be made with injection molding. This is a process where an injection molding machine uses an Archimedes-type screw to force melted plastic pellets into a mold or cavity. The plastic then forms the shape of the mold as it cools and hardens. These new uses for the Archimedes screw have sometimes resulted in a subtle change to its original design.
Modern Archimedes screws are not always completely encased in a cylinder. They often have an open top, so the bottom 2/3 of the cylinder exist, but the top does not. This is particularly useful in sewage treatment plants where you need to pump water up into a sewage treatment plant and you want to avoid blockages. So you can imagine that if the water comes from a river or comes from otherwise, you don't want to have a blockage inside an enclosed cylinder that you then have to stop, take apart, and spend a lot of time with downtime. This you can just stop it, remove the debris, and carry on. So that's the main improvement that we've made to it, but the basic design has not changed since the time of Archimedes.
Unchanged for thousands of years, the Archimedes screw is truly a wicked invention. Can we build a water pump using a garden hose? We're going to need a large diameter PVC pipe, some clear plastic hose, and some duct tape. We take the clear plastic hose and wrap it tightly around the PVC pipe. Allow the end of the pipe to overhang the end of the tube by approximately 2 centimeters. Tightly wrap the hose along the entire length of the tube, fastening into place with duct tape as you go. Our pump rotates, and after a few turns, water starts to come out of the top end of the pipe. As the pipe rotates, the neck of the hose dips into the water. As it continues around, a little of the water falls into the bottom of the pipe. As this movement repeats, the water continues to fall down the tube, which actually means it travels up the pipe until finally it pours out from the top of the tube. Can we build a water pump using a garden hose? Yes, we can. Wicked challenge smashed. The guitar has been one of the most popular instruments for thousands of years. The first use of the word guitar has been traced back to the 14th century. But just when was the instrument itself introduced?
What we know as the modern-day guitar evolved from a number of ancient instruments, and a form of stringed instrument has existed in a lot of cultures many, many years ago. Probably the earliest one dates back to Egypt 4,000 years ago.
As time progressed, we began to see a large adaptation in the size, shape and sound of the guitar.
Probably the most significant instrument that we now recognise as a guitar was traced back to Spain in the 16th century, and it again evolved into a different shape. The body of the guitar was larger, the actual dip in the middle was increased, and this changed the sound of a guitar. But again, more strings were added, and in different countries, as it spread into Europe and different areas, they had their variations.
Guitar makers finally abandoned the extravagant shapes and started creating the form of the models that we now see today.
The guitar as an instrument actually was most associated with sort of working class people, and even gypsies and travellers and people who played music as part of their culture, as part of their community, which meant that actually for the classical music community it took a while for it to be accepted.
However, with the vast developments and changes among technology and societies, it didn't take long for the guitar to be accepted by all.
And then, of course, in the 20th century, you had the electric guitar, and that changed everything. Obviously, with the introduction of electricity and technologies that allowed that new sound to be made.
Over the years of its use, the guitar has been known as a member of the family of musical instruments called chordophones, which is simply a group of stringed instruments. But just how are these wicked inventions made? Gibson guitars are recognised for their quality by musicians all around the world, and great care is taken to achieve this during the manufacturing process. But how is a dovetail crucial to the guitar's design? Let's find out.
Gibson was founded in 1894 when Orville Gibson began building some very interesting stringed instruments in his own workshop. So Gibson has been building stringed instruments now for 122 years.
Wood is delivered to the factory in the form of long planks, which are processed to cut them down to a usable size. The back of the guitar is made from two sections, which are cut from the same piece of wood. These pieces are then book matched, a process which makes sure the grain patterns mirror each other.
The inspection and sorting out of those materials is the first key step to make sure that we're building the world-class instrument we need to build.
These two pieces of wood are placed on a table, which clamps them together and attempts to shine a light through the joining edge. If no light can be seen, then the seam is perfectly flush. A roller is used to apply glue to the inside seams. This ensures glue is spread evenly along the length of the wood. The back strips are then placed into a press for 50 minutes, which applies pressure on the join so that the wood segments are fitted together as tightly as possible. The press rotates so the operator can remove the back strip, which has been in the press the longest. This is placed on a conveyor belt, which takes the segments through a thickness sander. This machine quickly sands the top surface to ensure it is level and smooth. Next, a drill press is used to cut out the decorative rosette around the sound hole, which is seen around the top of a finished guitar. The cutout rosette is then sanded and filled with two strips of plastic. To prepare the rib sets, which form the sides of the guitar body, they are sent through the thickness sander twice. This ensures a quality surface which can then be graded. Two similar ribs are matched together in the grading process. These are taped together so that they can't be mixed up. Then a bandsaw cuts away the excess wood from the edges of both the ribs. This means that the ribs have identical sizes and will fit together perfectly. The rib sets are then placed into a bath of hot water, where they are allowed to soak for around 10 minutes. This softens the tannins within the wood, making it softer and more flexible, which means it can be bent further without splintering. Individually, each piece of wood is bent into the jig, where it will sit for 5 minutes. When the jig opens up, the dried ribs are removed. To combine the two ribs, a headlock and tailpiece are glued into place. These are thicker bits of wood that will attach around the joins between the two ribs and give the design its overall strength. These are clamped in place and set aside whilst the glue dries. Next, a template is used to mark the exact location of the pilot holes, which are then drilled using a pillar drill. The rib set is then placed into a body mould and screwed into place. A rib spreader is placed in the centre to force the ribs outwards, ensuring they take the exact shape of the guitar's body. The body mould is then placed into a parabolic sander, which sands the radius of the top and backs into the ribs. The top and back are then routed out so that the braces fit perfectly into the rib set. To fix the top and back faces to the rib set, glue is applied so the respective sides of the rib set in turn. The faces can then be positioned on the rib set and the guitar body is placed into a press for 20 minutes whilst the glue dries. Once the body is removed from the press, the edges are sanded down to make sure everything is flush and flat, ready for the dovetail neck joint. The notch for the dovetail neck joint is created by fixing the guitar body to a jig, which then passes along a router. The result is a notch the exact size of the peg, which will be created later. Next, every side of the guitar is sanded down in order to make all the surfaces smooth and flush. Hand sanders are used to give greater control of which surfaces are sanded more than others. To assemble the top half of the guitar, ears are glued to the peg head before it is carved out. The neck now enters another router machine, where it is roughly carved into its final shape. To create the peg head, a sheet of metal is bolted over a block of wood. The router then uses a computer design to perfectly cut these to shape, whilst engraving the manufacturer's name onto the metal plate. To join the neck and body, the neck has a dovetail peg carved into it. This will fit perfectly into the notch, which was carved into the body earlier. Frets are then punched into the fretboard. This is what a musician uses to navigate the board through touch. The fretboard is then glued to the neck using a press. At last, the neck can then be glued to the body. Glue is added to the dovetail joints of both pieces, then they are lined up and pressed together. Clamps are used to hold them in place whilst the glue dries. To colour the guitar, various oils are sprayed into the wood. The iconic sunburst colour is applied to the top, back and sides, with tobacco brown colours sprayed onto the neck to give a contrasting appearance. To protect the wood, 7 coats of nitrocellulose lacquer are applied. This is a time-consuming process, as each layer must dry before the next can be added. The guitars are left to rest for 5 days, giving plenty of time for the lacquer to dry. The final components are now added to the guitar. To attach the bridge, it is measured against the guitar and the outline scored into the paint. A heat lamp is used to soften the paint and lacquer to remove it before the bridge is fixed to the guitar. The entire guitar is then buffed using another cotton wheel and wax abrasives. Finally, the strings are added to the guitar and it can be tuned for the very first time. The builders play a small tune on the guitar to make sure everything feels and sounds perfect. A final inspection is completed to check the guitar is spotless before it is placed in its case, ready to be shipped to musicians around the world. The guitar, truly a wicked invention. So, there you have it, a dash through the hidden history, super science, and amazing manufacture of products that you use every day, but have never realised their amazing backgrounds. Ice skates, the Archimedes screw, and guitars, all wicked inventions.